So welcome to part 2 of lecture 12. Where we left at the last part is I stated this theorem here, is that if we have a linear map and if it is invertible, then its inverse is unique. And so I quickly want to prove that. It's pretty not too difficult. So let's say that S1 and S2 are linear maps from W to V that are inverses of T. And our goal is to show that S1 and S2 are the same map. Okay, well, let's think about what this means. Well, S1 is the same thing as the map S1 composed with the identity. Okay, so this is the composed with the identity on W. Okay, but now we know because S2 is inverse of T, we can replace this identity with S1 T S2. Okay, so that follows. We're just replacing I with this function because this function is also the identity on W. Now we have the associative property of linear maps. Okay, so here this is the associative property. And then, because we regrouped S1 through ST, this is the identity composed with S2, right? And so this is the identity on V, but this is going to be the exact same thing as the function S2. So if we look at these two linear maps, S1 and S2, we're getting the same map on both sides. So that completes our proof. Okay, so because of this theorem, it says that if a linear map is invertible, its inverse is unique. So we can actually have some special notation to denote this unique inverse. So if it's invertible, we're letting t raised to the power of -1. That's a -1 there. Let me make that a little clearer. Raised to the power of -1 denotes its unique inverse. Okay, so the next theorem gives us a way to check whether a map is invertible, because if you were trying to use the definition to see that it's invertible, you have to check that both of these conditions are true over here. But the theorem tells us, well, to check whether a linear map is invertible, it's enough to show that the map is both injective and surjective. Now, one direction, I'm going to actually let you go look in the textbook. See the textbook. So it's only a couple paragraphs to show that if it's invertible, then the function t is injective and surjective. So I wanted to actually walk you through the proof of the reverse direction to show why this is true. And because it's a little bit more subtle, and it's just I want to kind of help you through the details here. Okay, so remember now we're given a map from V to W. That's kind of what we're given, a linear map. We're given that it's injective and surjective. To show that it's invertible, we need to find another linear map that when S and T are composed with each other, we get identities. Okay, and so this is how the map is defined. Okay, so we're going to define a map from W to V by taking W to SW, where SW is in V satisfies the property that it's the element that gets mapped to W by T. Okay, so there's a little bit to unpack here, so let me just write this out. Right? So since T is surjective, there is an X in there's an X in V such that Tx is equal to W. Okay, so here we're using the surjective property. So T is surjective. So if I take any element W inside of W, there's some element if I take any element W, little w and W, I can find some X that maps to it. Okay, and moreover, we also know that because T is injective, there is only one x in V such that Tx is equal to W. Okay, so what happens here is the map S sends W to this X. Okay, so that's really how this map is defined. So when you're taking a W in, a little w in W, it's being mapped to the thing in V that, that T maps it to. Okay, maps it back. Okay, that's kind of what we're saying here. So it takes a little time to kind of unpack this definition, but if you go slowly, it's not difficult. Okay, and so first of all, we're going to check that it behaves like the identity. Okay, now by the way that we defined our function as, if we take something in W and we stick it in, well, by definition, it goes, it takes T as W, and this is equal to W for all W in W. Okay, right? Because S of W gets sent to the thing that T takes W to. Okay, so that we've kind of cooked things up so it behaves like the identity on W. And now we need to prove that it behaves like the identity on V. So for any V in V, okay, we can now look at T evaluated at S composed with T with V. Okay, so and using the associative property, this is the same thing as taking T composed with S evaluated at TV, and this guy here is equal to TV. And the reason this from here to here is just from the previous line. Okay, so by above, because here T composed with S, we just saw that it's the identity on W. Okay, so now we look at the fact here we have this function T evaluated at this vector is the same thing as T evaluated at this vector. And because T is injective, this means that S composed with T evaluated at B is equal to V. Okay. Oh, and I actually had left space for myself here. Let me just, so I don't need all of this. So what we have is that S composed with T is the identity on V. So we're almost there, right? Because this function S has the property that we want, that it behaves like the identity on either V or W. But we're missing a property. Namely, we're missing the property that the function S is actually also a linear map. So we need to check that property as well, that S is a linear map. And so let's go through how we would do this. Well, if we take any W1 and W2 in W, we can plug W1 in S, and we can plug W2 in S, and we get vectors here and a vector here, and we're adding them together. And this is a vector in V, this is a vector in V, so this is the same thing as T evaluated at S1. Okay, so T evaluated at S1 plus T evaluated at SW2. So this is the additive property of T, because T is a linear map, so we can do that. And now this is equal to W1 plus W2. And this is from the fact that T as W1 is equal to W1 and T as W2 is W2. Okay. Now, by definition, S evaluated at W1, W2 is the unique element of V that maps to W1 plus W2. But by our argument above here, we also see that this vector SW1 plus SW2 also maps to this vector. But by above, SW1 plus SW2 also maps to W1 plus W2. So because these things have to both map to the same thing, right? Because SW1 plus SW2 maps to W1 plus W2, and this is the unique element that maps to W1 plus W2, we thus have that SW1 plus S evaluated at W1 plus W2 is the same thing as SW1 plus SW2. Okay, so you may have to kind of slow down and go through this proof kind of line by line, but this will hopefully help you. And this only takes care of the additive part. So we're showing that S is an additive function. Now for homogeneity, it basically works the same. We're looking at the element lambda SW1. And that's a vector in V. We stick it into T because T is a linear map. We have by the homogeneity of T, we can factor out the lambda. And then T evaluated at SW1 is just W1 since TS behaves like the identity. So kind of the same argument that we have had above. On the other hand, S evaluated at lambda W1 was defined to be the unique element of V that's mapped to lambda W1. So we have two elements mapping to lambda W1. There's only one element that can have that property, so they have to be the same. So we have that lambda SW1 should be the same thing as S lambda W1. Okay, so this is giving us the homogeneity property that we needed. So that kind of finishes up the proof because we now show that S is a linear map from V to W. So this is kind of probably the complicated proof in today's lecture. In the next part, we'll do some examples and start talking about isomorphism.